Hi folks, this is tutorial number 29 in the playlist that is called Dynamic Scenario in 3D Experience Simulation and Animation. Now, the title of the video is specifying initial velocity with an impulsive force. The thing is that there is no provision for specifying initial conditions in the dynamic scenario interface of the 3D experience. So in order to specify initial velocity, if you have one, then somehow it has to be uh, uh, modeled so that the effect is actually uh, coming up with that initial velocity. I'll do that in the context of this very simple example. And in fact, there will be a follow-up tutorial, which I'll do it in a different context. We have a mass and spring system. Information is given here from elementary vibration. You know that the natural frequency is square root of k over m, and the period is going to be 2 pi over omega n, which is roughly 3.14 seconds. Now, suppose we want to solve this thing, but with the provision that uh, the block is standing at rest as it is, but it's given an initial velocity of 1 meter per second, obviously to the right, to the right. It's not obvious, but I'll make it to the right. Now, notice that based on the elementary differential equation, you can solve the problem, and specifying these two initial conditions, you come up with the actual solution, which is right here. It's the amplitude of the vibration from this rest condition is 0.5. And if you differentiate this thing, because of this 2, this 0.5 times 2 becomes a 1, and the amplitude of the velocity is going to be 1 meter per second. The question is, how do we tell the software that this is the initial velocity that we want? Let me remind you what we did in our dynamics class, where the impulse momentum equation was discussed. So when you have particles, and assuming that there are no assuming that there are no external forces, obviously uh, the uh, the momentum is conserved. Linear momentum is conserved, for example. But if we have an external force, such as a hammer that is hitting this mass, which is supported by a spring, then momentum is not conserved for the mass and the spring system. Obviously, for the whole system, it may be, but not for the mass and the spring system. And what we do is we say that the change in momentum is equal to the impulse. So assuming that everything starts from rest, the mass was at rest before the hit by the hammer. This is the impulse momentum equation. The change in momentum is going to be equal to the impulse, the integral of f of t dt. And for a short duration, we can replace f of t dt, the integral of it, with f dt. Okay, so assuming, and keep in mind that this first term is zero, the second term is zero in this expression, and therefore we have x dot plus, or mv naught equal to f dt. The moral of the story is that if you have f hat or f delta t, if you have that, and you have the mass of this, obviously the block here, you can actually get the initial velocity of the block. Okay, the point is that this instantaneous hit at a short duration, what it does, it really changes the initial velocity. Okay, hence, and let me read this thing. An impulse applied to a single degree of freedom mass spring system here is the same as applying initial condition with an initial velocity of f hat over m. And f hat is simply f delta t over m. So, in this problem, I'm going to solve it under two assumptions. One of them is that the value of the impulsive force is this height, roughly 31.85, and the application uh, takes place, duration of the application of the force is roughly 0.0314 second, which is 100th of the natural frequency of the system. Okay. Now, if you take that force, now notice that, by the way, the area under the curve, F times delta T, this 31.85 times 0.0314 will give you the value of F hat or M hat. It's going to be 1. Now, I can repeat this problem with having lower force, but a longer duration of a application of the force. The area is still the same, but this is comparable. It's not much smaller than Tn. So what I told you as far as simulating the initial velocity, as long as the duration of the application of the load is below, well below the natural period of the structure. Okay, so if you did it with this, and we will do it towards the end of the analysis, you see that the results are not going to be as we expect. There's going to be different amplitude for the displacement and for the velocity. Okay, so let's move on. The way I'm going to solve this problem is a block sitting on the ground, and we're going to put a spring between a point on the block and a fixed point here. I'll create a point here which the spring is supported between this point and the point on the block. Okay, these dimensions are only used if you want to repeat this thing, and uh, you want to have a record of what dimensions are used. This, what these dimensions are kind of irrelevant. However, I'll be using these numbers. Now, let me remind you that if f of t is constant, and it's not in our case, f of t was at the high value and then drops to 0. If f of t is constant, no problem. We know how to solve, how to specify f of t. If f of t is given by a single formula, nothing complicated, that if time is less than this, here is f. If time is between this and that, here's f. Uh, so it's not this, by a single formula. Okay, for example, just hypothetically, f of t equal to 5t or something like that. There's no problem. If there is an if statement involved there, we can use a rule, which is basically writing a couple of lines of code. The problem is that this doesn't work. You can do it. However, when it comes to simulating it, it doesn't recognize that there are those if statements within the rule. Okay. And I've already done videos on this before. So, however, this can be fixed by, instead of using a rule, we use a design table. I also have a tutorial on the design table in the same playlist where I did the different problem. Okay. So this is what I'm going to be using. Okay. Now, notice that we have to specify the properties of the spring. Uh, the stiffness is K. The reference length is 0 because I'm assuming that when the block is sitting right there, it's at the equilibrium position. There is no tension or compression of the spring, so therefore I'm going to assume the reference length is 0 in that position. And let me remind you how to do design table. So you go to the tools tab, and one of the items in the tools tab in the menu down below is design table. And when you click on it, it says, do you want to create design table from pre-existing file, which is no. I'm going to create it based on the existing parameters. So I'm going to use the second radio button, this one, okay, right there. And when we do that, it says, what do you want to go into that design table? Well, obviously, I want the time go there and the force to go there. See that? The excitation time, force excitation time, and force basically expression to go there. These two I wanted to go there. And it's going to create the design table for us, and we get a blank one. And then we can put our stuff here. So at time 0, 31.85. At time 0.0314, 31.85, and a slightly larger value, it's 0. So basically, it's that those two graphs that I showed you for impulse. And notice that when you do that, this icon here, this icon changes to a design table. Okay, so there it is. And We're going to run this thing twice, one with the symplectic Euler, then with DASSL integrator. The result will be pretty much the same. As far as the time duration, I'm going to use roughly 4 seconds, which is almost high, almost 3.14. So we want to capture at least one cycle of this oscillation. And what we do, if we plot the force, notice that over a very short period of time, force is uh, this large number, 31 point something, and then drops to zero. And then what happens is that the initial velocity, see that after it oscillates, you can see that the initial velocity is -1 right there. And the amplitude of the oscillation, this is the actual oscillation, the amplitude is 0.5. 0.5 amplitude oscillation is 1 meter per second. So it is what we expect. Okay, so let's go ahead and do it. I may have to go back to these slides later on to pick up some numbers. All right, so let's go ahead and insert the ground. Right click, insert, 3D part. This is going to be the ground. I'm going to rename this thing. I'm going to call this thing ground. And under instance, call it ground. It's just a box with those dimensions that I gave you. Let's go make it. Double click. Okay. So on a convenient plane, on that vertical plane, I will sketch a rectangle. Okay. The length of this rectangle, I made it based on my drawing, 1.2 meter. So this is going to be 1.2 meters. Okay. And the height of it, I decided to use, although it's totally irrelevant, I decided to use 0.05 meter. Okay, good. Now exit, and we pad it symmetrically in each direction by 0.025 meter, 0.025 meter, which is 25 millimeter. Oh, I need to use half of that though. No, 0.025 meter, which means the total. Oops, what did I do here? Let me go back there. Oh, the pad. Oh, not 0.05 millimeter meter. Okay, good. So this is going to be our basically gram. Now I'm going to create a point there, which is exactly halfway between these two, a point while I'm in the ground. So a point which has a height of uh, 0.1 meter. And let me see now for X, I use uh, exactly halfway in the middle. So that's going to be 600 millimeter or 0.6 meter. Okay, so oh, the, I'll use the negative so that it puts it on the other side. Okay, good. So right there, this is where the spring is going to be attached to the block. So I made I made this box at a point over there, exactly halfway between this. So we go all the way to the top and now insert our block. So right click, insert, 3D part. Let me call this thing the block, or this is the mass that's going to be oscillating. Block. And here's the block. Okay, so let's go ahead and do that. On the on that same vertical plane, I will sketch. Okay, so let's make a rectangle, which is 0.2 by 0.2 meters. So it's going to be 0.2 meter. Okay, And this dimension is also 6.2 meter, just 100 millimeter. Exit. And once again, I'm going to pad this thing symmetrically with the same thickness, which was 0.025 millimeter or 25 millimeter. There. Okay. Why don't I change the color of this? Graphics, change the color to orange. Okay, now while I'm in the block, I create a point exactly the centroid of that face. So the way to do that, I'm going to use the pull down menu, center of gravity. I don't know why they call it center of gravity of that face. That's going to be actually the centroid, like right there. Okay, very good. So now what we're going to do is we're going to bring this thing down. Well, that's pretty much it. We go all the way to the top. Let's put it in place. Let's bring this thing down, and I'm going to use the snap to do that. So manipulate, snap this point to that. Okay, good. So right now there are 2 points on top of each other here. One of them belongs to the ground, the other one belongs to the block. And later on, we're going to put a spring between them. Okay, good. Takes care of this. We go all the way to the top. Don't forget to save. Okay. Let's go all the way to the top, and we're gonna we can specify our what do you call our joint yeah, joints here. Let's fix actually the ground. Ground is fixed, and then we prismatic joint here. A prismatic joint. Okay, and I'm going to use this I don't know, this last one, last template. So it's going to be this. Okay, this edge and the edge of the block, this face and the face of the block, and I don't need this control mechanism, so I just delete that. You don't need it and say no. Okay, so what we have right now is a prismatic joint and a fixed part the ground. Okay, very good. We're done here, so we're gonna go to system design mechanical system design, where we specify our uh, mass properties. So let's go to mechanical system design. All right. Why don't we specify, for example, the masses? We go all the way to the right. See that at the very bottom? We go all the way to the right. Weight definition. Both red because we haven't done anything about it. So let's select the ground. The ground is stationary, so it really doesn't matter what we put in there, but we have to specify a mass. So click on the hyperlink, and we use properties of steel, which is going to be that much. Okay. And let me change my units here so that the mass is going to show up in kilogram instead of slugs. So let's see now, mass kilogram. Good. Okay. So now we're going to go and click on the block, declare the mass, use properties of steel, and I'm going to change that thing to be 1 kilogram. That was the mass of the block. And close it, and then close that. So now we have specified the mass of the block, which is 1 kilogram, and the mass of the ground, which is totally irrelevant, but we have to do that. Now let's go and create our spring. So you see that axial spring, you click on it. There are 2 points that I have here. The 2 points, one of them is on the ground right there. I take it from the tree sees here. The second one is from the block right there. So these are picked. And then we click on f of x here. Okay. The stiffness of it is 4 Newton per meter, but that's the same as this. Okay. And then make sure you click on the reference length, and if there's anything here, make it 0. It will be 0 because they're sitting on top of each other. Automatically, it will pick it to be 0, but I did it anyways. So we did define our spring element right there. Now let's go ahead and create our mechanism. Click on the mechanism representation, Say okay. And let's see what we've got here. Click on Mechanism Manager. You see that there's a fixed part. There's the prismatic one. And notice that it doesn't have any command associated with it, which is fine because we're going to apply force on it. And then there's a spring. Okay. So we say, okay, good. All right. So I don't think I've forgotten anything here. And that being the case, we go to our mechanical systems experience. And then we say, okay. And there's the name that it's going to give it, default name. Okay. So what we're going to do is, first of all, we're going to apply our, see that force law excitation right there? See that force law excitation? You click on this, and what we're going to do is we select the, for example, that point from the point on the support, on the point on in the ground, not the ground, on the block. So let's go pick that. For the support, we have to select the whole block. For the support, we have to select the whole block. And the application is going to be application point. It's easier for me to pick it from the tree. It's right here because they're sitting on top of each other. So this is belonging to the block. The direction is going to be in the direction of, for example, this thing. And if I want to apply force initially to the right, then I just reverse it. It really doesn't matter. Since I flipped it. And I don't worry, this one is not important here. It's not going to be used. We're going to change that. We say, okay. Now, notice that an excitation has been created here. Okay, right there. But we click on the tools, and I showed you these in the slides. You go all the way to the right, and you find the design table right there. Design table right there. You click on it. Second radio button, create a design table with the current parameter value. It says, well, what do you want to put in there? Well, I want the time to go in there, and I want the force to go in there. But in the slide that I showed you in the PowerPoint, there may have been other stuff here, but that's okay because I must have done something else there. And then we say, okay. Now what happens? It says you're about to open, start a Excel file. You want that? Yes. Let's give it time. Okay, good. Let's say okay. That's the default name. You can change it if you want to. Okay, good. So this is the spreadsheet. Okay, so click on the edit table. All right, 0, and this number is going to be 31.85 Newton, 31.85 Newton. And remember, I'm using the first case, so the time 0.0314, which is hundredth of the period, 0.0314, same value, 31.85. Yeah. And then finally, slightly larger value, 0.031, oops, wait a minute, 0.0315, drop it to 0. Okay, good. And probably even if you didn't include the last term, it may do that, but I did include it here. This is what I've done. Where is this? We did that, and there we are. This is what I inputted. Okay, so let's go back. Did I edit? Oh, right there. Yeah, right there. So make sure you save this. Make sure you save it. Can't close it. Save it, and then close it, and you're going to get a warning or a message that this is going to be synchronized with that. The mechanism is going to be synchronized with that. We say okay, and then we say okay now. Now notice what happens here. See, if I double click on this If I double click on this force excitation, notice that it does put a the icon for a spreadsheet there. Okay, you say fine, good, good. Now we're going to put a sensor up there. So let's go ahead and click on the scenario, a probe up there, probe, select this point. For example, you can select this point, you can select the point from the block, that center point from the block right there. I can do that. Good. And now we're going to create a dynamic scenario. Notice that we did create a law excitation, force excitation. We did create a probe, we send it to the right. And for parameter, first of all, let's use the symplectic Euler, 4 second. And I believe I increased these, or actually reduced these to uh, by a factor of 10 here. So I put down another 0 here, and you need to put another 0 there, because otherwise it comes back and says it's too small, etc. Say okay, that's pretty much it. And we're going to run it. Right click, run it. Right click on this, run it from here, or you scroll all the way to the right at this ribbon and then run it. Let say fine. Now notice that the spring does not show in the simulation because the reference length was 0. If you put a tiny little reference length there, actually you're going to see a spring there. But anyway, you don't have to. So this is going to go 1 oscillation, because I put down 4 second, which is very close to 3.14. And then it's going to stop, because we're doing it only for 4 seconds. It's a little bit more than 1 oscillation, maybe 1.5. Good. Okay, so now we go to view scenario results. Okay, let's first look at the force. The force must be at 31 point something, and then drop to 0. Okay. Incidentally, if I say deselect all, show me the force in the x direction, you may see negative here. That's because to the right, I applied the force going to the right, and to the right is actually negative x direction. Okay, fine. Now let's go and look at the position, the x position right here, x position of it, and that's going to give us the amplitude. This is going to give us the oscillation position. And oh, by the way, this unit here is a millimeter. So let me go ahead and change my velocities and things like that. That's okay. Let me close that. Go change the units. Units for displacement. Let me see now. Sort this out. Find the displacement. See if we can find the DIS. Oh, displacement, not in millimeter. Show it to me in meter, and also velocity. Show it to me in meter per second. I don't know what it is right now. Okay, velocity. Yeah, meter per second. That's good. Okay, so now let's go and do it now. Again, uh, view results. Okay, deselect everything. Show me the position, X position, and notice that maybe it still showed me the same thing. So let me run it again, and then look at it. Because it could be that because initially I ran it at millimeter when it comes to plotting it, use the initial result, but I ran it again so that I can look at the units of displacement in meter and unit of velocity in meter per second. So, almost done. Okay, so click on view scenario results. You select all, X component of the point right there. And now, or maybe length. Okay, so let me change the length to meter also. Let me go and change the length to, yeah, not millimeter, meter. Probably would have been okay even if I did it before. Okay, so let's try it one more time. Sorry. Okay. Please select all and then X point. That better be meter now. Yes. So notice that the oscillation goes between this range. So that is minus zero point 0.1 to uh, minus 1.1, which means that the total height from peak to peak is 1, and the amplitude is half of that, 0.5. Okay, now let's go and plot the velocity, not this, x linear velocity, and the amplitude will be actually from peak to peak is going to be 2, which means it agrees with the amplitude being 1 meter per second. Okay, now, you might say, well, what if we use a different solver? So double click on this thing, double click the scenario. We go to parameters, use instead of symplectic Euler, use DASSL. Say okay, and run it again, and we're going to get the same results. I will also go and change my spreadsheet. Uh, Remember I said that you can make the width of that impulse a hundredth of a period or make it period and see what the effect is. We're going to do that after this. I'm not going to change the solver though, because you can see that the result is going to be the same here. Okay, so let's go to view the results one more time. And let's look at the, for example, velocity, x linear velocity. You're going to get a total peak to peak of 2, which means amplitude of 1. Yeah, 1 to minus 1, total peak is 2, and the amplitude is half of that, which is 1. Now, if you want to change that, go to the design table, edit the table. Okay, so here I'm going to make this thing 3.14. 3.14. So I reduce this thing, I increase this thing by a factor of 100. So I'm going to reduce this thing by a factor of, I just want to check something here. Let's check this. Yeah, 0.3185. Yeah. So that's going to be 0.3185. 0.3185. Same to the next one, 0.3105. Okay. And then this one is going to be 3.15 and down to 0. So what I have done is I have actually given it this information. All right. So we say save, get out of this. After save, we get out. It says synchronize, and then we say okay, and now we're going to run it. And you're going to see that the amplitude are all going to be not the same as what you expect. This is using the ASSL, but it really doesn't matter. You saw that it gives the same results. I probably used too many points. Remember, by putting a 0 in the step size, you can already see that the amplitude of vibration is smaller. You can already see that. The other one went further to the right. See that? Okay, results. Incidentally, in tutorial 30, I will do a different problem, which shows you how to model the initial velocity. Deselect all, and if you look at the velocity, definitely you can see that the amplitude is not. That's because this, to get the velocity out of an impulsive force, the duration of the application must be much smaller than the natural period. Okay, and in this case, it's not. It's comparable to natural period. It'll run, but it's not going to give you the right answer. Okay, folks, good luck.